Episode 7, Rocket Propulsion. You're listening to SPEXcast. Welcome to SPEXcast, a podcast for discussing the science and technology of space exploration. I'm Phil, and joining me today we have TJ.
Hello.
Augie.
Hi, everyone.
And Ben.
How's it going?
All right, so today we're going to talk about rocket propulsion, specifically with chemical engines, rocket engines, and things like that. We have Ben joining us today. Ben, why don't you introduce yourself a little bit? This is your first time on the show.
Sure. My name's Ben. I'm a fourth-year mechanical engineering major here at RIT. I just got off of a co-op with Phil at SpaceX and the Propulsion Components Group.
Yeah, just a disclaimer, neither of us, even though they were interns, we don't speak for SpaceX in any way. We're
That's
just
true.
Sharing our knowledge, but not as representatives of the organization. Disclaimer, over.
Disclaimer.
Okay, so let's talk about rocket engines. Basically, they take in, we've talked about this a few times before in general terms, where they take in oxidizer, another propellant fuel, mix them together, blow them up, and we go into space, right? But so far we've treated it as like a black box where you have different kinds of fuel going in and then different thrusts coming out. But let's talk about how a rocket engine works. So the fuel goes in.
So before we go into fuel in, fuel out, the basic principle is that you're in space, there's no air, there's nothing to push against, can't push off the ground, stuff like that. So the main way that you change your momentum is that you take a certain amount of mass and you accelerate it the opposite way you want to go, and you generate an impulse.
Newton's third law of motion.
Exactly.
Right.
So all of the different propulsion methods, chemical, nuclear, electric, all have to do with taking a mass and accelerating it and sending it away from where you want to go. So going into the more specific ways we do that, chemical rockets are very easy in a way because you have the energy that you use to accelerate the fuel as well as the mass all in a nice little package that in a lot of cases you can just throw together. It combines, releases energy, and you just send it through a nozzle, right, and then you're moving.
So, like, after you release the energy through release the chemical energy, you also push that used-up mass out the back.
Exactly.
Right? That's what you're saying. And that works for launch stages within atmospheres as well.
No, exactly.
Yeah.
If you actually look at the formula, being in the atmosphere and pushing against the air actually decreases your efficiency.
Interesting. So, going off of that, can you guys explain one thing that I've always kind of wondered and I'm not sure about? Why do engines in space have bigger engine bells, like bigger nozzles at the end than launch stages within the atmosphere?
All right, so I'll give it a shot. It has to do with how the mass coming out of the nozzle expands. When you have a bigger nozzle, you get more expansion. And you need this because you like you said, you can't push off anything in a vacuum, right?
So the expanding mass that comes out the end of the engine is pushing against the nozzle, and that's where it's transferring its force to the rocket itself?
Yeah, so basically you're starting with a dense, slow-moving mass, and you're going to expand that into a less dense, fast-moving mass. Right, and that's where you're getting your momentum change. You're taking all that heat energy and that hot, dense gas, expanding it out.
But what does that have to do with the nozzles?
Into speed. And so with the nozzles, the specific design is called a de Laval nozzle. That is a specific shape where it goes in from, regular width, curves in, and then expands outward.
Okay.
And so with that de Laval nozzles, those are the most efficient nozzles for basically expanding that gas. And with upper stages with the large bells, you want to match the pressure of the gas to the pressure of the ambient pressure. So in space there's zero ambient pressure basically.
So you want the biggest
nozzle. And so you want to optimize to basically zero pressure. So basically the way I like to think of it is that the gas is compressed and it wants to go outwards.
Yeah.
Right? But you have the walls of the combustion chamber, the walls of the nozzle. And basically you want to expand the walls outward so that instead of pushing out against the walls, it's pushing itself directly out of the engine backwards.
Okay.
And so you want to match the length of the nozzle so that when when it reaches the end of the nozzle, it doesn't want to go out anymore. It just wants to go straight back out of the rocket.
And when you're inside the atmosphere, you have the added pressure from the atmosphere itself. So you have a smaller... So the less pressure outside,
your
the bigger
ambient
the
pressure
valve.
is different. So, right, it's like a nozzle that expands out to ambient pressure of, sea level is different than one that's 100,000 feet or space. So, what you actually happens is you actually optimize not for sea level and not for upper atmosphere for first stage. You want to do that. You kind of choose a pressure in the middle, so you're actually less efficient when you take off, and then you reach optimum efficiency, and then you become a little less efficient towards the end of the first stage of burn.
And then once you enter the atmosphere, you stage, and you have a whole new nozzle to work with.
Yeah, and there's also a trade-off because of nozzle diameter. Because ideally, I think mathematically, you could have an infinite nozzle, and that would get you the most efficiency because you go up to zero pressure.
Right.
But obviously, anything that you build in the real world of infinite size has infinite mass. And when you come to spacecraft, you want to save mass wherever you can.
Yeah.
There's actually an optimal size of you expand it to 90-95%, and you cut it out.
95%. Yeah.
You cut off the nozzle because you're going to be gaining too much extra weight and mass to make up for the efficiency gains.
So what about rockets that have 3 stages or multiple stages other than just 2 stages where you separate and then you use the bigger bell nozzle?
Are you referring to 3 inline stages
3,
like the Saturn V?
Exactly, yeah. So does that optimize the middle range somewhere in there?
So that just has to do with where the payload is destined to go. The 3 stages on the Saturn V, the Saturn V is designed to go to the moon, right? So you need 1 stage to get up to speed in the atmosphere, a 2nd stage to get to orbit around the Earth, and then the 3rd stage to get to the moon.
So it's really all about weight savings or mass savings. It's not so much about optimizing the nozzle size for the 2nd or 3rd stage.
Yeah.
Okay.
So with staging, you're optimizing the total vehicle, and you're basically optimizing the mass fraction. But that does give you the opportunity for each engine, for each stage, to optimize the design for the range of flight that it'll fly through.
Sure.
So you can be more efficient in that.
So did the Saturn V do that, though, I guess is my question? Did they have a larger bell size for the 2nd and 3rd stages than the 1st?
I believe so.
They used a different fuel.
Yeah, you're using different fuel and a different engine type. So the F1s are on the 1st stage, and you have J2s for the 2nd and 3rd. So there's, there are different chamber pressures. So you can't compare absolute bell size between them.
Does bell size change with fuel as well? I mean, I guess it depends.
It's all about pressure. So you want to take your chamber pressure and then match that with your ambient pressure to whatever you want.
And your chamber pressure will obviously change if you have different.
And you optimize for different fuels, yeah.
Okay. Are they that much different? The different types of fuels?
Yeah, they are. They are. A rocket that's designed to use hydrogen is a lot different than a rocket that's designed to use RP1 or kerosene. The same principle is there, but they definitely, it's not interchangeable. You can't just swap out the hydrogen for RP1.
It's a different chemical reaction.
Right.
Like totally different parameters. So, is it as simple as taking the fuel in, putting it in a small spot, and then lighting it on fire, like sparking it, igniting it? How does the ignition take place? That's what always baffled me.
Well, again,
in general terms,
different applications do it differently, right? It is like an ignition. You have your fuel, you have your oxidizer, and you need a heat source. SpaceX specifically uses hypergol, or a chemical that reacts with the oxidizer and heats up, and that's what causes the ignition source. But I believe that did the shuttle use sparks?
Yeah, the shuttle uses sparkers. SpaceX uses TEA-TAB,
right,
which are 2 different chemicals that combine and becomes pyrophoric.
Hypergol, yeah.
They're hypergolic.
Hypergol is the general term. TTAB is the actual substance that they use.
And so they're pyrophoric, which means that you pump them into the chamber with the oxidizer, and they'll react spontaneously with that. And that gives you your initial heat, and then bring in the kerosene, and then the engine started.
So the kerosene and the oxygen when they're mixed, automatically ignite, right? That would be the hypergolic?
No, so kerosene and oxygen are very combustible, but not hypergolic. That
So you
heat
ignite
comes from
it
TA
The liquid oxygen is hypergolic.
with TEA and TAB.
Right. It's a hypergol substance,
Right.
but you need another hypergol to make that ignition, and RP1 is not.
And in what stage of the rocket engine, like what is that part called? Did you say that? So when you ignite the liquid oxygen, what is that part of the rocket engine?
That's going to be in the combustion chamber.
Just the combustion chamber. That's what that makes sense.
Yep.
Cool. So where does the liquid fuel come into play? Like, so you have the hypergol ignites the liquid oxygen, and then the liquid oxygen, once ignited, uses RP1 or whatever fuel mixed together. Like, I'm a little fuzzy on that. Once it's ignited, then you stop adding hypergol, and the two things mix together and burn. Is that correct?
Yeah, pretty much.
For the most part.
From what I've read, your TAB is your starter, so you're going to basically inject a small amount of that.
From outside the engine?
Outside the engine, it happens inside the engine. You're going to be inserting into the combustion chamber, but you have a very small volume of that. That reacts with the oxygen, and you also have oxygen and RP1 mixed in kind of a not gaseous state, but as in like the liquid drops kind of fine spray, and then everything ignites. So the initial reaction is between the oxygen and the TAB, but then once everything's heated up, then the kerosene can catch. But ignition in the rocket engine is really, it's one of the most challenging things to kind of analyze and predict. You basically, for the past 30, 40 years, just had to go out and pump stuff in and watch it explode or ignite and actually run. Now we have, more advanced computer models, and we can kind of guess. There was a video released by SpaceX about their computational fluid dynamics of Raptor, and that's with methane and liquid oxygen. And that is a very, very relatively simple reaction where you have a basic hydrocarbon and a basic oxidizer mixing together. But I think you get something like 150 different potential reactions from that in the combustion chamber that you ought to simulate. And once you
it's not just the two things that you're using. There's also a bunch of different possible outcomes from the reaction.
So like at the end result, like, in chemistry, you're taking these two chemicals combined, then you're getting CO2 and H2O.
Right.
That's not what actually exists in the chamber. And your exhaust actually might have different percentages. Usually what happens is that those are going to be like a percentage point or 0.1% of a percentage point. And so you can assume that, okay, you're going to get your exhaust because it's going to be consistent.
What if I were to look at all the different engines that are out there, for example, the Space Shuttle's engine and the Falcon 9 engines and Blue Origin's engines and everything. If I wanted to look at them and I had a rocket and I needed an engine for it, how would I judge the performance of all these different types? And how would I choose which one would be best for my application? Is as easy as it is in Kerbal Space Program, where you look at the ISP and the weight and you look at your thrust to weight ratio or something?
Well, I was going to talk about ISP.
Yeah.
That's kind of like a main, metric of comparing different engines. Because, you have engines like the F1, which I don't know if you've ever seen it, but it's gigantic, and the whole nozzle is probably, I don't know, like they're 20 feet or something like that.
Whoa, the nozzle?
Yeah.
Yeah, they're pretty big.
Compared to the Merlin M1D, which is, much smaller. So ISP is a good way to put a consistent unit between different engines so that you compare their performance.
So you can compare two things apples to apples using ISP?
Right. Yep. And then also you can look at an engine's thrust too. Like using the example between the F1 and the M1D. The F1 had 1.5 million pounds force of thrust, and the M1D comparatively is about 170,000 pounds of thrust.
Right.
When you compare the ISP, the M1D actually has a slightly better ISP at 280 compared to like 260 seconds is the units for ISP.
Right. So, it doesn't put out as much thrust. It's a little bit more efficient. obviously smaller. So if you pack 9 of them together, you can get a pretty good rocket.
Right. Yeah,
it's
and
easier and cheaper to build as well, right? I mean, that's kind of the big advantage, isn't it?
yeah, it's modular, right? So you can put, like, look at what they're doing with the Falcon Heavy. You know, they're just, instead of 9, they're putting 27 so that you can get more payload capacity.
Yeah, and ISP is, the measure of the efficiency. You can look at ISP, thrust to weight ratio, total thrust, but you have to at least consider all of the different variables when you're designing your rocket. You can look at, ion engines, which have fantastic ISP, 10 times better than a chemical rocket, but you can't build a first stage of a launch vehicle with that. You're not going to get the amount of thrust. Also, depending on the stage of the rocket that this engine's going on, you might want to go for a higher thrust, lower efficiency engine, because that's what you need when you have to take all the mass of the rocket and get it out of the atmosphere. You have to worry about optimizing for atmospheric efficiency. You can, not use as complicated fuels. I mean, with the Saturn V, you had RP1 on the first stage, but hydrogen on the second and third. And so you can focus on, the more engineering system applications and requirements. And then once you're in orbit, you can focus on efficiency.
I see. One thing I wanted to ask is how can you take an engine idea or concept of a certain type of engine and make it more efficient? What are some things you can do besides changing the nozzle that you can optimize on? Is there what parts?
Yeah. Well, as an example, SpaceX actually just recently did this with their SES-9 flight. In order to upgrade from the original Falcon 9 version, they wanted to get more thrust to push it up to the 170,000 pounds force. In order to do that, they densified the propellants, which basically means that they can pack more fuel and more fuel. Both, right?
I guess so.
Yeah, both, right? So you can pack more into the rocket, and SpaceX did it specifically so that they could have enough fuel to land.
So is that more a denser fuel going into the engine, or a denser fuel, more fuel for the same amount of volume in your fuel tank?
It's both. It increases the efficiency, and they also have a higher quantity of fuel. Yeah,
I didn't realize it increased the efficiency as well.
Yeah, because they increased their thrust capacity. It was about 145,000 to 170,000.
Yeah, right. If you look at the rocket engine thrust equation, mass flow rate and ISP are very critical to that. So when you densify the propellants, the same turbopumps in the engine, every turn you can kind of think of it as bringing more mass into the chamber. Mm-hmm. So that's how you get more thrust to that.
Interesting. And they did that by cooling it down, and that's how they densified it. But I guess
that's right.
If it's liquid, that's really the only way to do it, right? Mm-hmm. Is there a difference? What if you had solid fuels are even denser than liquid fuels? Can we burn them the same way?
So what you find with solid rockets is that they have a lot more thrust. So the fuel is a lot denser. Their efficiency is much poorer, though.
Why?
Just through the chemical reactions. Also, you're not getting complete combustion. And the chamber pressure is a little bit lower as well. You actually get a lot of bits of solid fuel and liquid fuel. Ideally, you're just getting a pure expanded gas.
Right.
You're actually going to get clumps of liquid, metal, aluminum kind of stuff in there. Very nasty to breathe in, but that does take a chunk out of your efficiency. And you're not going to have a consistent fuel. So your chemical reaction happening through the entire solid rocket is going to be slightly different. So those things are big challenges with solid rockets. You just have to, go and you got to thoroughly mix it. You got to be very careful with your chemistry of that.
You can't throttle the engine either. So if you have a solid rocket, once you combust it, you're going until it's empty. Basically, you can't cut it back down. So if you wanted to, maybe land a first stage or something like that, there'd be no way to throttle the engine so you could, hover slam and hit a landing spot.
And that's because if you burn through the fuel, you're burning through the solid, so you can't control that reaction, right?
So you actually can. So you can't toggle a solid rocket booster on and off, because once you light it, it's basically going to burn through its fuel. But you can actually design the inner pattern. So you just kind of visually shown a false assumption that with an SRB, the fuel burns from the bottom to the top. It actually burns from the inside out. The entire tube is burning on the inside, and the entire tube is the combustion chamber. And by changing the shape and doing different patterns, you can actually change the thrust. One of the very common things they do when you use those boosters is that you want to get the rocket going as fast as possible, and then you're going to reach max Q, max pressure, where there's a lot of aerodynamic force on the rocket. Ideally, you might want to throttle back the thrust, get past that little bump, and then speed up again. And so what they'll do is design the booster so that when they reach roughly around max Q, minimize the amount of thrust, and then pick up back again.
So you can change the thrust over the ascent,
yes,
but that's fixed and decided when you're
manufacturing.
You can't do that based on autonomous software that helps throttle.
No, exactly. And it's very, I don't want to call it witchcraft because it's very intense science. But, it's all based on the interior surface area. So as the rocket burns outside, the inner circle surface area increases. And by doing a different pattern, star shapes, different polygonal shapes is what they actually do, you can change how that surface area changes over time.
And it plays back like the music box. For the same shape, it plays back the same way roughly every time.
Every time you make that. Also, with segmented boosters, you can do a thing where each segment might have a different shape, and you can kind of get a little bit different thrust through that. So there is a lot of design and kind of fiddling you can do with SRBs, but they're nowhere near as flexible as liquid engines.
So while we're still on the topic of cryogenically cooling liquid, basically fuel or oxidizers versus solid-based engines, what's the current limit at which we cool these fuel and oxidizers? So basically, are we cooling it down to the point where it's right before a solid, or are we cooling it just to as cold as we can get it because that's as dense as it will be?
In theory, right, it would be the most efficient if you could have it
just before the solid,
right before the solid, right? But recently, SpaceX did have issues with cooling down with their facilities and the launch pad, and specifically in keeping it that cold while it's just sitting there, right?
Right, but are they cooling it down as cold as they can get, or are they cooling it down just before the solidifying point?
I'm not sure what the actual number is.
So I don't know the number either, but you can make a couple assumptions with liquid oxygen. They're trying to get that right above the freezing point.
Oh, do you have a number for what the freezing point is, just to give me an idea?
I'm thinking in the low 20s. So you're looking at that. With RP1, they actually can't get it to the freezing point. They don't want to, because it starts, instead of acting like a liquid that you can pump easily, it starts to sludge up. So it's still liquid, it's not a solid yet. They'll start to sludge up, and then it doesn't work well with the turbo pumps. And so there's a practical lower limit.
I didn't even think about that. As colder the denser it gets, the turbo pump kind of has to work harder.
Right.
Mm-hmm. So the freezing point of liquid oxygen is about negative 360 degrees Fahrenheit.
Yeah, which is negative 220 Celsius, and then the SpaceX cools theirs down to negative 206 Celsius. Do you have the same information?
Yeah, I remember hearing 350, negative 350 Fahrenheit.
Okay, so 10 Fahrenheit off, right? So that probably is their limit, and if they get too close, they might be worried about temperature fluctuations and ending up with you don't want some part of it solid, and you definitely don't want sludge.
And the way they're cooling it, at least one of the ways to cool this liquid is to cool it with huge machines outside of the vehicle, then pump really cold stuff into the tanks, but then it warms up on the launch pad.
And they let it boil out, so they have ways where as it gets hotter, it automatically boils out, and they can keep pumping more fuel in. So when the rocket launches, it's totally full of fuel and ready to go.
Is that what the smoke is on the launch pad?
Yes, that also is a big challenge with this fuel densification. So before, when they had the liquid oxygen right below the boiling point, it would boil off, and then that phase change would actually keep the rest of the fuel cool. What happens now is that because it's right below freezing, that entire column of fuel will heat up until right below boiling and then start boiling off. And so the boil off is not keeping everything at their desired temperature. So that's one of the reasons that they're having a lot of trouble, is that once it's in the tank, every second it's there, it's getting farther away from ideal temperature, and that boil off is no longer helping.
Right. So when you say it's at the boil off temperature, a liquid will heat up until that temperature and then stay at that temperature until all of it is a gas.
Exactly. Yes.
It'll heat up. Okay.
Yeah.
That's interesting. It'd be interesting to see if this densification method really continues on. Are there more ways to densify a propellant? I don't think so.
Not without changing the chemical combustion process, right?
Going back to your original question was modifying the engine to be more efficient, right? So changing the density of propellants is one way. Changing the fuel ratio is another. Most engines don't combust at the stoichiometric ratio, which is where all of the fuel and oxidizer turns into its resultant products. They actually change that mostly because you want to take the lighter element, that be fuel or oxidizer. You actually want more of that. So the key thing in the thrust formula is the exhaust velocity. So you can kind of think of the entire process of the engine generating a certain amount of momentum through all the different processes, and that the rest of the mass flow rate going through that is given that velocity. So you want to increase that velocity. So if you actually pump in more, say, fuel with a hydrolox engine, you pump in more hydrogen, which is lighter, that will actually increase the ISP counterintuitively.
All right. Well, Ben's got to go. So thanks for joining us, Ben. We're going to keep going on this conversation, but thanks a lot.
Thanks, guys.
Thanks for stopping by.
Okay, so now that Ben left, we can break out the cool things. No, unfortunately, I had to go. So, do you guys want to talk a little bit about external propulsion, which is essentially, blasting laser or microwave beams at a rocket and putting them in orbit completely without having any chemical rockets or anything like that. Just totally ground-based propulsion.
I've heard of this, and I know a few people that are really excited about it, but I have some questions or issues. I'd like you guys to kind of explain it and talk about the benefits a little bit more before I kind of...
So external propulsion is a fantastic idea.
Yeah.
Unfortunately, I'm going to upset Phil and go into the equations. So with a rocket from a vehicle design, the hugest issue is called the rocket equation.
It doesn't apply if you don't have an engine on it, right?
That is because you have to bring your fuel, every ounce of fuel that you bring, you have to use fuel to bring it up there. External propulsion changes all that. So basically, there's two types I've seen. One that you bring your reaction mass with you. So you'll have usually hydrogen in the actual vehicle, and then all your energy comes from outside. Also for launch vehicles, something that's really cool is that they take the air and through something similar to a ramjet or a scramjet, compress that air, and then using external energy, heat that up and get thrust from that.
Interesting. External energy?
Yeah, so you'd beam energy either from laser or microwave or some external source.
Yeah.
And then send that to the craft. And with microwaves and lasers, it's easier, where you can send it and then have it directly react with mass on the spacecraft.
Yeah, so there are two things there. One is the light isn't really attenuated over time, especially not in space. So like when you beam it, it's not like sound where it decays over time. It does because it gets more diffuse.
You're going to get some inverse square law losses, but if you tightly culminate your laser, you can minimize those.
But then the farther away you go, you have to be that much more precise with where you point it.
You really would have to be spot on. So it's hard enough nowadays beaming up and down from satellites, let alone following a moving rocket where you have all sorts of clouds and atmospheric changes. And the Earth is spinning. There's just so many things going on.
Yeah. So if you look at it just as a solution for launch vehicles, right, which is what I've seen is proposed, the pointing is still extremely difficult. I mean, if anyone's watched a webcast of a rocket launch, even they can't keep the camera tracked. And if you're using external propulsion, you have to make it very well aimed on the vehicle.
If you're not aimed on the vehicle, it doesn't go.
Exactly. So that's a very big challenge. Something I personally believe that we can overcome over time. But also, you're going to be in the atmosphere and you're taking an energy source, and ideally, you're sending energy. And it's going to hit the spacecraft in such a way that it heats up whatever fuel source you have. Unfortunately, it's traveling through said fuel source.
Oh, you're saying the air would be the fuel source, so you'd be...
In one of them, it's taking in air. So you're compressing the air and then heating that up.
Okay.
But, your microwaves are going through the air and through your laser. So you're going to have energy losses. So you're looking at, inefficiencies from the energy spreading out, inefficiencies from loss to the air, and then inefficiencies in how you collect all that energy and put it into your fuel. And so you end up having massive, massive power requirements. And you actually look at the power outputted by a rocket is insane. You're looking at multiple hundreds of megawatts, sometimes gigawatts of power. And that's because these chemical reactions are insanely energetic.
Yeah.
And rocket engines are very, very efficient at converting that chemical energy into thrust. And so you have to basically take all that to electricity and then pump that through the air, through loss, and then turn it back into mechanical energy.
Right. I was going to put that in perspective. Like, for example, the Hoover Dam only produces a couple gigawatts of energy, doesn't it? And most, power plants, only the bigger ones are in the gigawatt range. Okay. So if you're saying a rocket would require gigawatts of energy beamed, that's an entire power plant that could potentially power a city only for that rocket launch.
Right. And what's, I guess, interesting to me after hearing you talk about it, TJ, is that you said it may still be something that's feasible in the future, but if it's really going to take that much energy, it probably will never be feasible in the future unless we get, nuclear fusion or some way to get almost unlimited energy for very low cost. Because if you think about, reusable rockets being successful, like completely 100%, which is more likely now than external propulsion, then you look at the cost of that and estimate, under $500,000 to refuel that rocket, then will it ever be worthwhile to spend gigawatts of microwave radiation on a rocket?
I mean, I guess one advantage of reusable crafts be sort of like going hand in hand with beamed energy, because you don't need an engine, so you just beam it up, it falls back down.
Right. It would still totally be reusable, but really the cost of energy is still very, very high, and relative for gigawatts of energy. So it doesn't seem like in the future that cost is going to come down significantly to produce gigawatts of energy.
So I don't want to discount the significant challenges, but if you look at it from a different perspective, the Hoover Dam is producing those gigawatts consistently over time. And so what happens is with the rocket launch, you're getting a ton of energy coming through within 5-10 minutes. And so, your power plant that could be powering a city is going to have to power that rocket for 10 minutes. But then the rest of the time it could be powering a city. There's, energy storage methods, capacitors, things like that. So that's not really a showstopper. But another way to look at it is that when you're not in the rocket equation, when a Saturn V launching, it's millions of pounds at takeoff. If you have an external propulsion system that does the same amount of thrust as a Saturn V, instead of launching your millions of pounds of fuel with your 100 tons of payload, you're suddenly launching thousands of tons of payload at the beginning, which is a huge increase, which is something external propulsion can do. But there's a ton of challenges, especially with tracking and all that.
One thing I wanted to talk about this, and it's super quick. This is only a way to accelerate, but if you're trying to go, for example, interplanetary, if you want to accelerate for half the time, the rest of the time you have to decelerate, and there's no way to, unless you have a beam station at your destination, there's no way to slow down. So I guess it would be a cool way if you brought some of your, only like the deceleration fuel required, and had like a station on the moon, and you'd beam it, and it would be like a speed boost.
Or you could stick with, chemical rockets and beam the chemical rockets up there, still entirely full of fuel. And then once they get up there, they can ignite and continue on their way.
Right.
So it'd be kind of like a first stage, second stage thing in there.
Yeah. I don't want to jump into too much sci-fi, but in the movie Avatar, their spaceship, they actually took the time to do a big backstory and actually work out the physics. And so in their far future, reality, that big spaceship that takes them from Earth to another star is laser powered to launch from Earth to Alpha Centauri, and then they have a fuel station or a fuel on board that will burn over however many years to slow down.
Right.
And then they fill up with fuel there and use the fuel to take off from Alpha Centauri, and then use the lasers to slow down.
Oh, that's interesting.
But again, like lasers when you're using lasers as the momentum carrier, that means that the object has to be moving away from you.
Yeah. So it's really interesting. I don't think it's going to be feasible in my lifetime, but it's really cool to think about. And I think there's already like people thinking about this seriously, and there's some cool applications for sure. Mm-hmm. Okay, so I think that's going to wrap up this episode on spacecraft propulsion. Thanks for listening. We'll be back next week with another discussion on space exploration, science, and technology. If you would like to share your thoughts on rocket propulsion, or if you have questions or requests for another discussion topic, send an email to SPEXcast@gmail.com or tweet to us at RITSpecs. If you want to hear more, consider subscribing to us through iTunes or your favorite podcast app. All past episodes are also available to download from our website. This podcast is made possible by RIT Specs, a space exploration student-faculty research organization at the Rochester Institute of Technology. Special thanks to the Interactive Learning Grant Program for giving us the tools to promote student and faculty engagement outside the classroom. Our music is by Kevin Hartnell. This has been SPEXcast. We'll see you next week.